AP Physics, the mechanics. The first one gives you the graph of a velocity versus time. You can look at, like, at the beginning, this velocity is some positive, and then it decreases, end up being some negative velocity. So up here, the area under this curve right there would represent how far we went to the right, and then this would represent how far we went to the left as far as areas. And so if you kind of look at this graph, we are going to go to the right, and then we're going to go to the left, and they're symmetrical. So we actually, after, 1.5 seconds, and then another 1.5 seconds, we're actually back to where we started. So I think this one actually makes a lot of sense. Again, the slope here is velocity, and the concavity is acceleration, where up here, the area under the curve is the displacement, and the slope is the acceleration. All right, an object is dropped from rest, and how far it travels during the first 6 seconds. So we get our classic h equals 1/2 gt squared, and we just plug in. Now, if you wanted to know the height after 6 seconds, you would have to do this. Remember, when we just kind of jump to the 1/2 gt squared, that is the distance an object falls, not actually the height of the object. The height of the object is the full-blown equation h equals h naught plus v naught t minus 1/2 gt squared. And in this case, since it was dropped, we got rid of the v naught. But this bottom one would really be the height as a function of time, where that term just represents how far something has fallen in a certain time. Number 3, so we have this ball, it comes in, hits the ground, and bounces off. The angle of incidence is the same as the angle of reflection. Those angles are the same. So if you think about the x component of momentum, there's no change in the x. So that must mean there's no force in the x direction. However, the y component, you were going down, and then you were going up. So the net force, the impulse, has to be upwards, right? The change in momentum was only upwards. So it's got to be E. All right, this one, they want you to be able to do this really fast because they give it to you in the abstract. Which rope is the strongest, C, B, or A? And clearly C is the right answer. C, just think about it, C is responsible for pulling all 6 kilograms. Okay? C doesn't even know that there are ropes B and A even exist. C simply knows I'm pulling something that has a total mass, if we make M1, then it's got a total mass of 6 kilograms. B is responsible for pulling 5, A is responsible for pulling 3, and so if you think of the ratios here, if C is the full force, which it is, then B is 5/6 because it's pulling 5/6 of the total, and A is pulling half. So if you actually wanted to find the forces, A would be F over 2, B would be 5/6 of F, where C is full-blown F. Again, it's the ratio of the masses, which it's responsible for pulling, can break down the forces really quick. So certainly C's got to be the strongest. Okay, we're going to use this graph on both 5 and 6. On 5, we simply want the acceleration, and we're looking at a force versus time graph. So if I want to find the acceleration at 2 seconds, I just come up here and find the force at 2 seconds. F equals ma, the force is 2, the mass is 3, the acceleration thus is 4/3. However, if I want to find the speed, I got to figure out what happened during these 2 seconds. Well, now I'm thinking about the area under the curve is the impulse, right? The accumulation of force over time is impulse. So I find the area, and I find out that the area is 4, and then I set that equal to m delta v. Now in this case, the impulse is just the momentum because the object started at rest. So I just set 4 equal to 3 times v, and I get 4/3 for v. And again, I understand these are both 4/3. They're different units. They don't really have anything to do with each other. They just both happen to be numerically the same. All right, 7, trying to trick you. They say the plane is frictionless. If it's frictionless, then a ball and a block and a board are all the same thing. It doesn't matter. A ball needs friction to roll. Without friction, the ball will not roll down the ramp. It will just slide down the ramp like it was like really, really slippery ice. It won't rotate at all. So when we do this, it's just mgh equals 1/2 mv squared, and we solve for the velocity. Again, no friction, no roll. Now this one, Okay, and now the plane does have friction, so it will roll. What's the speed of the velocity to center mass? Remember, when it says velocity to center mass, it's just saying what is the velocity of the ball. Whenever we say the velocity of the ball, we are always talking about the velocity of the center mass of the ball. So now we do E1 equals E2, and we include the rotational energy piece of 1/2 I omega squared. And so if you kind of go through that, then you get this when you solve for V. Again, this one, no friction, no roll. The ball might as well be just a box. Once it does have friction, it will roll and it will gain some rotational kinetic energy, as well as our normal translational or linear kinetic energy. All right, this is just vectors. This box is in equilibrium. So if you think about a free body diagram, you got weight down, or mg down. You got T2 up and right and T1 left. So if you balance the forces, T2 is pulling to the right, T1 is pulling left. Those have to be equal. T2 is pulling up, and the weight is down. And if you solve, you end up getting the tension in the string is 300. All right, so they're giving you these free body diagrams in this story, and then they ask you some questions about it. So if we take a look at this, stupid. Oh, sorry, my bad, not stupid. The normal force is right there. The normal force is wrong here. This is dumb. The normal force does not go up. The normal force is normal. Normal means perpendicular, okay? This, look, they tricked you. They switched those things. We know that mg sine theta is down the ramp and mg cosine theta is into the ramp. So this one also wrong. Okay, now let's look back here. Which figure best represents if it's accelerating up the ramp? Well, if it's got to be going up the ramp, dude, we got to have some big force that's pulling up the ramp that beats friction and gravity down the ramp. Okay, so we get E. And then these are tricks. Which figure best represents at rest and at constant speed? Remember, a free body diagram of something at rest looks identical to a free body diagram of something moving at constant speed. Free body diagrams talk about forces with accelerations. Well, the acceleration of something at rest is 0, and the acceleration of something moving at constant speed is 0. So you cannot tell the difference between something at rest and something moving at constant speed based on a free body diagram. And if we look at C, we get a nice balance, right? Friction is up, mg sine theta would be down. If those things are balanced, it will be moving at a constant speed, or it'll be at rest. Okay? So this one, friction would be down, gravity would be down. How would this one actually be doing anything? I mean, this would have to be moving up, but how would it be moving up with no applied force? So this one is just kind of silly on how it's constructed. Okay? Okay, so they give you some momentum equation. This is kind of going backwards. Normally, they give us some force equation and we integrate it or find the area under the curve to find the impulse given. But if this is true, this is the other version of that calculus. The force is also the rate at which we change our momentum. And so this is just power rule. Take the derivative of the momentum and that will find you the force. Remember, think, momentum is mv, force is ma. So the force clearly is the derivative of momentum. And again, it is the opposite of this, right? Fundamental theorem of calculus talks about how the integral and the derivative are inverses of each other. I don't really like these questions, but this is all about like elliptical orbits. And so you're going around in this circular orbit and you fire your engine at P, and now you're moving faster. Faster when closer, so then slower when you're farther away here. Again, it's all about conserving angular momentum. Closer is faster. So when you start to slow down, you got to go further away. And so it ends up being D. I think these questions are a little tricky. They don't ask them often, but that would create that elliptical orbit. 15. This is a ball moving in a circle at a constant speed. Well, if you're whipping this thing around in a circle and you're not increasing its speed, then you're not doing any work. You're simply changing its direction, right? The work is equal to the change in kinetic energy. You're not speeding it up. So keeping it moving in a circle, yep, your force is inward, but you're not actually doing any work. This is like a conversion type deal where they give you some information about the radius, the distance, the time. Again, if you went 20 meters in 5 seconds, you must be going 4 meters per second. And then we can convert that to an angular speed where we know V equals omega r, which is the same thing as saying omega is V over r. All right, this one, we've seen this before. This is a skater who hits this board. The board is not bolted in, so there's no external force, which means both of these guys are conserved. A linear momentum is conserved in collisions. Angular momentum is conserved in collisions. Yes, the skater hitting this board will make the board and the skater move to the right, but it'll also make the board and the skater rotate. So both of these are conserved. Again, linear momentum is conserved with no external force. There's no friction. The board isn't bolted in like a merry-go-round, and then there's no external torque because the torque that the skater applies to the board is equal to the torque that the board applies to the skater. Basically, going back to Newton's third law. I don't know why they asked this question. It seemed just very easy, just straightforward. Like that's the equation for the period of a pendulum, and then you just chuck it in. This is going a little bit backwards. They tell you the period is 2, so we know this is true on the relationship between period and omega. If the period is 2, omega must be pi, and then boom, we know this is a possible equation for what the angle would look like. Some original angle, and then it's a cosine or a sine, and in this case, since they told us the period was 2, they told us omega was pi, so you just chuck pi in there. Atwood machine, we know this is what it looks like, right? The big mass here is mg down. This is mg opposing it. That's the net force causing the mass to accelerate. And just solve for A. This is a non-linear spring, so we're going to have to integrate. So integrate kx squared and get 1/3 kx cubed. Again, non-linear springs, don't use Hooke's law, don't use 1/2 kx squared. All right, total kinetic energy. This is basically saying, this is a question really of, hey, energy is a scalar. So the total energy of this system before is take that energy and add it to that energy and then get the total. Momentum is a vector. This is the momentum vertically, and this is the momentum horizontally before, which also is the momentum afterwards. Considering collisions, we conserve momentum. But momentum is a vector. So you cannot just say 3 plus 4 here. You have to do vectors and do 3 squared plus 4 squared equals 5 squared. Again, momentum is a vector. Can't just add them. Kinetic energy is a scalar. Yes, the total energy is just the addition of the two energies before. Calculus question, they give you the position as a function of time, and we want to know the acceleration, so just take 2 derivatives. When the girl launches the ball that way, the ball will also apply a force to the girl who's attached to the boat and make the boat go that way. But however, once the dude catches the ball, he applies a force on the ball, and the ball applies a force to him to the left, and it will make the boat then stop afterwards. Eventually, there will not be a change in momentum. The boat's position will move right and then stop because the center mass of the board moved, and so the board's position had to move a little bit to balance that out because we know that the center of mass can't actually move. Okay? I think there was another multiple choice question like about Romeo and Juliet, and Romeo kind of walking on a plank towards Juliet, and what the board does. Again, the center mass can't move, so the system has to shift itself. This is just looking at the pulley. We know that for the pulley to turn, T2 has to have a bigger torque than T1. Torques are forces with lever arms, so this is the torque of T2 versus the torque of T1, and that causes the system to experience some angular acceleration. This is a little calculus. We know that the work is the accumulation of force over time. So the work is this area under this curve. We're taking an object from way, 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 way and bringing it to R2. The work done is the area under the curve. 28, I would suggest drawing a free body diagram. So here we got these up here. We got you pushing into the page, or into the wall pushing back. Friction is going up, which is preventing the thing from sliding down because gravity is down, wanting it to be pulled down. So if you look at this, then you can just make some substitution. You can figure out how hard you have to push FA for it to stay stationary. So just do a substitution. Total trick question. We know that this is the period formula for a mass on a spring, and you take it to some new planet, which has no effect whatsoever, right? Gravity does not affect springs. The mass of the spring and the stiffness of the spring affect the period of a spring. All right, we're taking this motor and we're lifting something. We know powers work over time. Work can be the change in kinetic energy. In this case, it's just mgh. So you're just lifting something. So this is the work you do in a certain amount of time, and then you can figure out how high you can lift it. This thing is going in simple harmonic motion, and we want to find the speed at equilibrium. Okay, we know that at equilibrium, all of the energy is kinetic, and at the end, all of the energy is elastic. So just set them equal to each other and find the velocity, which is the maximum velocity, at equilibrium. We're doing this lab, and we're looking at lightweight plastic balls, and it's definitely going to experience some drag forces. So when you figure out things are weird, it's because the acceleration of the plastic balls is not uniform because of the drag force. You have to include drag force if you're actually doing a lab, certainly with lightweight plastic balls. 33, okay, we talked about the optimal angle. If you launch something from the ground, it's going to go like, and if you want to make it go the farthest, you better launch it at 45. Because we need it to go high, so we need V naught sine theta to be big. But we want it to go far, so we got to be going fast, so we need V cosine theta to be big. Well, to maximize it, a ground-to-ground launch, you need those to be the same. So an angle of 45 is ideal. But if you already have some built-in height, the optimal angle is going to be slightly less than 45. And that equation is actually very difficult. There was a PDF in the module if you want to look at it, but not something you're responsible for. All right, 34. I don't know. I maybe was a little harsh here. Maybe it's not really a stupid question, and they're certainly not all wrong. There's the right answer. It is vertically upward, and I'm going to show you a little something to explain why. And down here I say, well, it's really just because of the fact that it's moving in a circle. So immediately when the tire picks up the stone, boom, the stone is moving in a circle, and the acceleration is upward, thus the force on it is upward. And I do say the rock is also accelerated from rest, so it's got to have some tangential acceleration, and that's, I don't know, you got to define what it means by initially. Certainly the rock gets some tangential acceleration because the rock does speed up, but when you start talking about, I'm going to erase this comment, initially it is right away, it is only upward. And I'll show you here in a second. The escape velocity, that's just an escape velocity formula. Escape velocity, orbital velocity, you got to know it. If you know it, then boom, you're done. Because if you just double the mass, you increase the velocity by the square root of 2, because v is related to square root of m. Okay, so let's go back here. I'm going to actually show you a cycloid, which is a really fun curve that you might explore if you were in a physics class or a calc class. But there's a cycloid, and I think it does a pretty good job if you look at right away when that object gets, at the very bottom. If you look at the acceleration right away at the beginning, it is straight up. And so the acceleration, thus the force on the rock as the tire picks it up, is actually straight upwards. Okay, hopefully that visual kind of helps you out. But remember, they're always trying to get you to say that they know, that you know, that the acceleration and the force of an object moving in circular motion is inward. Inward, inward, inward. If an object is moving in a circle, there's a force making it move in a circle, and the direction must be inward.